Hi everyone, I'm Shane from CPS Virginia Tech. Today my topic is wide voltage range high efficiency Sigma converter 48 volt VRM with faster transient response. Here shows the 48 volt rack power architecture. With this kind of architecture, we have three challenges. The first one is high efficiency and high power density 48 volt VRM. Since we have very limited space on the motherboard, and also we need to put the VRM very close to the DDR, CPU, and GPU. And the second challenge is we have wide voltage range of operation, especially for GPU, it will operate at 0.6 volt to 1 volt. And the third challenge is high current demands. For GPU application, people now are even talking about more than 1000 ampere. And based on these three challenges, we propose our single-stage Sigma converter. The single-stage Sigma converter is an input series and output parallel converter, which means it will have power sharing between the two converters. And we want the majority of power through efficient ALC DCX, and the small buck converter is used just to regulate the output voltage. And here shows the Sigma converter operating region. For the nominal condition and most of our operating regions, we will operate the ALC at the resonant frequency, which is the most efficient point. And for region 2 and region 3, we will operate the ALC at a larger and smaller than the resonant frequency. The frequency range can be seen here. It's from 800 kHz to 1.5 MHz, which is still a narrow frequency range. And for the ALC part, the matrix transformer is used. The winding is shown here. And since we need some gain control of the ALC part, we design an integrated leakage inductance with the transformer. So here shows the winding of the transformer. And in order to integrate the inductor together with the transformer, we can first share the same winding and then integrate the inductor to the transformer. And in this way, we have a controllable leakage with minimum footprint, and the inductance value will be determined by our gain requirement. This one is our hardware prototype of the wide voltage range Sigma converter. And here we can see we can achieve CVS operation for both primary side device and the secondary device. Also, we can achieve very high power density, 700 watt per inch cube. And here shows the thermal result, thermal performance of the Sigma converter. The highest temperature is 65 degrees, which is pretty good. And here shows the efficiency of our Sigma converter. So compared with two-stage solution, we can increase about 1% peak efficiency. Also, when we increase the output current, the efficiency drop for Sigma converter is much smaller than the two-stage solution. Compared with STM and the Victory solution, we can have about a 2% peak efficiency increase. So after this, our question is how to control the Sigma converter. So after building the small signal model, and we can get the output impedance of the Sigma converter with enhanced physical control as this one. And here we can see the DC part of this output impedance equals to the Ri over 1 plus Nd, which means in order to achieve constant load line requirement, the sensing gain needs to change with duty cycle, which means the power stage will always changing. In order to avoid this one, we developed some new, we added the active Dupe control to enhance the physical control, which is shown here. We add one additional current feedback as well as a variable gain to our voltage feedback. In this way, by controlling the Dupe, the Dupe gain, we can achieve constant load line at a different operating point. And here is the result for point 1 and point 2, which is at nominal condition. By changing the Dupe gain, we can achieve constant load line here, which is about 1 millimeter. And for point 3 and point 4, which is our worst point, we can also achieve constant load line by changing our G-Dupe value. And here we show the transient performance of the sigma converter with the control method we proposed. For point 1, and we can see even with the IDT equals to 3000 ampere per microsecond, we can find here we don't have overshoot and undershoot. Also, during transient, the two converter have good current sharing. Point 2 is very similar to point 1. And for point 3, and with the IDT equal to 3000 ampere per microseconds, we can see there is very small overshoot and undershoot. And this overshoot and undershoot is within the requirement of VR13. And for point 4, we have very similar performance with point 3. So just to give a quick summary, we have proposed the design method for our sigma converter to operate efficiently over a wide voltage range. And we achieve high efficiency, 95%, and high power density, 700 watt per inch cube. And we also investigate a different control strategy for wide voltage range, 48 volt sigma converter. And we get the conclusion that the V-square control is a suitable choice. Also, we finished the AVP design with enhanced V-square control to achieve constant load line requirement. And our future work is, first, we need to finish our hardware testing to verify our control method. And second, we want to consider the output current to be higher value. Also, we want to consider some peak current requirement for the sigma converter. That's all of my presentation. Thank you.